All right, hope you guys can all hear me. Let me know if you have any trouble hearing me. Okay, so let's start with calculator number one. Um, okay, so number one reads, temperature of coffee in a cup at time t minutes is modeled by a decreasing differential function c, where c of t is measured in degrees Celsius for t values between 0 and 12. Selected values of c of t are given in the table shown. Approximate c prime of 5 using average rate of change of c over the intervals between 3 and 7. Show the work that leads to your answer and include units of measure. So we know that c of t is in terms of degrees Celsius. We know c prime is talking about the rate of change of temperature. So normally we would find the derivative if we had a function to find the derivative, but the next best thing, just because we have a limited amount of data, we can still find rate of change, but it just asks us to approximate, so we can just do slope. Okay. And our units of measure is degrees Celsius per minute. Or B, use left-Riemann sum with 3 subintervals indicated by the data in the table to approximate the value of the definite integral from 0 to 12. So we'll do that first. Left-Riemann sum, 3 subintervals. So we're going to add up areas of rectangles, 3 rectangles. So we'll start off with the definite integral from 0 to 12, uppercase c of t dt, can be approximated using 3 rectangles. If I subtract the minutes in each interval, that will give me the width of each rectangle. So 3 minus 0 is 3, 7 minus 3 is 4, 12 minus 7 is 5. Width times height, the width of my first rectangle is 3. The height of my first rectangle is 100. Second rectangle, width of 4, height of 85. Third rectangle, width of 5, because 12 minus 7 is 5, and a height of 69. Use your calculator, add up those values. We get 985. And now we want to talk about what is this going to tell us? 1/12 of the integral from 0 to 12 of C of t dt. So this is basically in the form of 1 over b minus a, integral from a to b of our function. And essentially, we're taking this value and we're dividing it by 12. So this 985 is actually going to be degrees times minutes. But if we take degrees times minutes and we divide it by minutes, we'll be back down to degrees Celsius. So this is what this is telling us, is that this is telling us, well, this will tell us the average temperature after we added all this up and divided it by 12. Okay, they did not ask us to find the average temperature, but if we were to find it, we would do 985. Just want to kind of give you a perspective here. 985 divided by 12. Which is 82.083 degrees Celsius. And that is telling us the average temperature across all these temperatures here. And this should make sense, right? Between largest is 100, the smallest is 55, and somewhere between is the average. So 82.083 degrees. I know they're not asking for it, but just to connect with the idea that this is average value theorem, and this represents the average temperature in degrees Celsius over this 12-minute period. Part C, between 12 and 20 minutes, between 12 and 20 minutes, the rate of change of temperature is modeled by C prime. So this is now telling us the rate at which temperature is changing each minute. Find the temperature of the coffee at time t equals 20. Show the setup for your calculations. So this is where we like to use the formula final equals initial plus displacement. If we have an anchor point, and the anchor point is actually something that we can pull from our table. So we have an anchor point, we have a rate of change, which we can basically find displacement, and we can use those two combined to tell us our final destination or our final value. So we're going to use this particle motion formula that we've just basically a rearranging of first theorem, where we know final position is equal to initial position plus displacements. But we can use it in a variety of applications, and this is one of them, where if I want to find my final temperature, I can figure out my initial temperature. Well, we have the temperature at the 12th minute, so we can use that as our anchor point. And then from 12 to 20 minutes, we have the rate of change, which we can accumulate this rate of change over time to figure out how much the temperature has changed and add that to the last known value from our table. So our initial, we can start off at 12 because we're leaving off at 12. And then we can just bridge that gap between 12 and 20 minutes, C prime. Okay, so use your calculator here, math 9 from 12 to 20, and then plug in your C prime in your calculator. And we know that at the 12th minute, temperature is 55 degrees. And math 9. So I have y1 holding my C prime, negative 24.55 e to the 0.01 x divided by x. And then that gave me the change in temperature between the 12th and 20th minute. And if I know that my temperature has dropped 14 degrees after the 12th minute, I can figure out what the temperature is at the 20th minute. Okay, for the model defined in part C, it can be shown that C double prime of t is equal to the given function here. For t between 12 and 20, determine whether the temperature of the coffee is changing at a decreasing rate or at an increasing rate. So we can try any value between 12 and 20. And you can also imagine too, right? You don't even have to plug it in with your calculator. You can just tell that, well, 20, this is always going to give me positive. E raised to anything is always positive. 100 minus 12, 100 minus 20, that's also positive. So this whole thing is positive. So because my C double prime of t is always positive, I can say that the rate of change of coffee is increasing. Or is changing at an increasing rate. So since C double prime of t is greater than 0, the rate of change of coffee is changing at an increasing rate. Okay, number 2. Number 2, still a calculator problem. Particle motion here. A particle moves along the x-axis so that its velocity at time t greater than or equal to 0 is given by v of t. There is one time t for particle r in the interval from 0 to 2 when the particle is at rest or not moving. Find this time. For t between 0 and t sub r, is the particle moving to the right or to the left? Give a reason for your answer. So if we want to figure out where the particle is moving, that's when our velocity is equal to 0. So for part A, I'm going to set my v of t equal to 0. And because this is a calculator question, I'm going to make the calculator do it for me. Typed it into Y2. I'm going to graph it, sim 6. I'm looking for a value between 0 and 2, so I'm looking for a positive value there. If I do zoom 1, let me just draw a box around that region and have an easier time looking for my x-intercept after that. Let me see, doing this right. Natural log of, oh, sorry, I typed it in wrong. Natural log of x squared minus 4x plus 5. Yeah, I typed in 4x squared, should be 4x squared minus 4x plus 5. And then minus 0.2x. Okay. Okay. X-intercept, second trace 0. We can point to the left, hit enter, and then go to a point on the right, hit enter. Okay, 1.42. And between 0 and 1.42, we can see that our velocity function is clearly above the x-axis. Above the x-axis means moving right, below means moving left, since this particle is moving along the x-axis. So if it's moving along the x-axis, positive would mean to the right and negative would mean to the left. So between 0 and 1.426, the particle is moving to the right. One second. For t between 0 and 1.426, particles moving to the right, since v of t is greater than 0. My velocity function is clearly above the x-axis in this time interval here. From 0 to 1.426, velocity is clearly positive. Part B, find the acceleration of the particle at time t equals 1.5. So we know acceleration is the derivative of velocity. And because we have our calculator, we don't have to do this by hand. We can do math 8 on our velocity function and evaluate the acceleration at 1.5. So currently I have my velocity stored under y2. So if we do math 8, trace y2, and then at x equals 1.5. So I'm making the calculator find the derivative, get it down to the acceleration level, and then plug in the 1.5. Negative 0.999. is the speed of the particle increasing or decreasing at time t equals 1.5. So anytime we're looking for increasing or decreasing speed, we are comparing the signs between velocity and acceleration. If velocity and acceleration have the same signs, then speed is increasing. If velocity and acceleration have opposite signs, then speed is decreasing. So we know our acceleration is negative 0.999, and we can also find the velocity at 1.5. So if you do alpha trace y1, this is the velocity level. Sorry, y2, I have it stored under y2. Right now, y2 is holding that velocity function. If I do parentheses 1.5, it'll enter 1.5 in for the velocity function. It'll give me either positive or negative, and this time it gives me negative. So I have negative acceleration, I have negative velocity. These are both the same signs, and so therefore speed is increasing. But if one is positive and the other is negative, then speed will be decreasing. So speed of particle is increasing at t equals 1.5, since v of 1.5 is less than 0, and a of 1.5 is also less than 0, and velocity and acceleration share the same signs. Okay, part C, for the position of the particle is x sub t. And its position at t equals 1 is x of 1 equals negative 3. Find the position of the particle at time t equals 4. So this is a good setup for that particle motion that we've been seeing a lot of, where final equals initial plus displacement. We have our anchor point, we have our target destination point, and then we also have displacement, which is just the integral of velocity. So we can set up final position equals initial plus displacement. I'm trying to find x of 4. I have x of 1, and I just have to figure out how much progress has this particle made in that time interval from 1 to 4. So we can do math 9 on our velocity function from 1 to 4. I got 0.1971. So we know the particle is starting at negative 3, and it's going to move to the right 0.1971. So it's going to end up on the x-axis at negative 2.803. Part D, find the total distance traveled by the particle over this time interval from 1 to 4. Show the setup for your calculation. So total distance, we know it's just that absolute value formula, the definite integral of our absolute value of velocity function. So we can set it up that way, and the rest is just calculator entering into our calculator. And then to get to the absolute value feature, you can do math number ABS, math number ABS, and they can store the velocity function inside the absolute value bar. Alpha trace, I'll have it sorted under Y2. It may take a second to return you a value. Right, 0.958. All right, number 3. The depth of, so now we're going into our non-calculator section. So the rest of the exam, no calculators, 3, 4, 5, and 6 on the AB test, no calculated. The depth of seawater at location can be modeled by the function h that satisfies the differential equation. dH dt equals 1/2 h minus 1 cosine of t over 2. H is measured in feet and t is measured in hours after noon. It is known, and noon is represented as t equals 0. It is known that h of 0 equals 4. Okay, a portion of the slope field for the differential equation is provided. Sketch the solution curve y equals h of t through the point 0,4. So find order pair 0,4 on your slope field, on your function. And then here, this is easy. You're just kind of tracing the graph along the flow that the slope field is providing you. So you're just kind of following along the path of the slope field. That's it. Okay, so that's part A, just sketching that portion. Part B, between 0 and 5, it can be shown that h of t is greater than 1. So the depth yeah, h of t is greater than 1. For the value of t between 0 and 5, at which h has, or find the value of 5 at which h has the critical point. Determine whether the critical point corresponds to a relative minimum, a relative maximum, or neither. Justify your answer. So we know that if we want to find a critical point, that's going to come from the derivative. So we're going to have to set h prime equal to 0. And we know that dH dt is basically at the h prime level. So we just have to set dH dt equal to 0. So to find critical point, we're going to set dH dt equal to 0. Now, you may see two different things here. You can think of this as, oh, I'm going to set this equal to 0. I'm going to set this equal to 0. But if you notice, it says that h of t is greater than 1. So if it's greater than 1, that means we're not going to have to worry about a critical point here because it's always going to be greater than 1. It could be like, 1.1 minus 1 or 2.1 minus 1. H is, if we set that equal to 0, we'll get h equals 1, and h of t is always greater than 1. So we can ignore this. Basically, this is telling us that there is no critical point because h of t is starting off at a value higher than 1. So we can ignore that piece of it. However, we can find critical point at with the cosine t over 2. So we'll set that piece equal to 0. I like that. But the reason that we're not looking at the h minus 1 is because of that statement. Okay, so cosine of t over 2, that's the same thing as saying when is we can solve for t over 2 and looking for where cosine is equal to 0, inverse cosine is 0. So looking for radian measures where cosine is equal to 0, and cosine is equal to 0 at pi over 2, 3 pi over 2. I'm going to keep going, 5 pi over 2. We're dividing by 2, so I'm just going to go a little further. So let's say pi over 2, 3 pi over 2, and if I go another rotation around, basically adding 2 pi to pi over 2, I get 5 pi over 2. I may not need that much, but just want to go a little further just for peace of mind. Okay, so if I want to solve for t, let me just multiply everything through by 2. I get pi. Multiply the 2 through. 2's cancel out. I'm left with 3 pi, and then I'm left with 5 pi. Oh, sorry. There's something here. Oh, right. Okay. So pi, 3 pi, and 5 pi. But we're only looking at t-values between 0 and 5. So 3 pi is going to be, around like 15, and 5 pi is going to be around like, oh, sorry, 9. 3 times 3 is 9. 5 times 3 is 15. So we only have to worry about pi being the only critical point that's going to live between 0 and 5. So here's my h prime sign line. And I'm just going to test my values against my h prime to see whether I get a positive or negative slope so I can make my decision about whether this critical point is a relative max or relative min. So I'm going to test. This is without a calculator here, so it's easier if I can find something that can be a unit circle value that I can test. So I'm going to say, okay, an easy value between 0 and pi would be pi over 2. So if I insert pi over 2 in for t, again, no need to worry about h because we know h is always going to be greater than 1, so we know this is always going to give us a positive value. But if I plug pi over 2 in for t, I basically get cosine of pi over 4. Cosine of pi over 4 is definitely positive, so we know this interval is rising. And then between pi and 5, I can choose 3 pi over 2. I plug 3 pi over 2 in, and I get cosine of 3 pi because the 2's cancel out. Basically, I'm sorry, I get cosine of 3 pi over 4. And we know cosine in the second quadrant is going to be negative. So we know that at pi, we must be looking at a relative maximum. So based off of our slope sign line, know that there's a relative max at t equals pi, since h prime changes from positive to negative. All right, part C is our big separation of variable solving differential equation problem. Use separation of variables to find y equals h of t, the particular solution for a differential equation. And we're going to go through all of our steps, separating our variables. We ultimately want our h's on the left, our t's on the right, take the antiderivative. We're going to solve for c, and then we're going to solve for h. Okay, cross multiply. If I think of this whole thing as my numerator, if I cross multiply, I'll get dh equals that's what I like to do first. I like to get my dh and dt's in their final locations, and then I can ask myself, okay, how can I get my variables nicely separated? The h minus 1 is what's out of place. I'm going to divide that h minus 1 over, but everything else I'll just move on. I'll leave on the right side, right? I only want what is absolutely necessary on the left side. So I'm just going to move that h minus 1 over. Okay, full separation of variables. H is on the left, T is on the right. We're ready to move into our integral procedure. But it looks like both sides requires its own use substitution. The left side is going to be the H minus 1 being our U value. And the right side is going to be that T over 2 or 1/2 T being our U value. So we're basically going to be kind of working on two separate problems, taking its antiderivative, resolving it, and then we'll come back together with the steps after we get both of these up to the function level. I replace dh with du. I replace h minus 1 with u, and this is very clearly recognizable as the natural log rule. So we know this is just going to turn into natural log absolute value of u, and then we can bring back our original variable. Okay, so we can wait to come back to that once we resolve the right side. This one is also use substitution, but this one, our u value is t over 2 or 1/2 t. Uh, Max, I just saw your chat message. If you can send me a picture of what you typed in on Remind, maybe I can look at it in a little bit later, and I can um, see if I can verify what could be the issue. Okay, derivative du over dt is equal to 1/2. Solve for dt. I'm replacing dt with 2 du. And looks like that leftover coefficient is just going to cancel out with the 1/2 that's already there. So looks like the 1/2 and 2 will just cancel each other out. I'm just left with integral of cosine of u. And we know cosine turns into sine. And then replace the u back in terms of t. Okay, so we have our results from both of the integral procedures on the left side and the right side. And now we can set these equal to each other. And then we can focus on our final two tasks, which is solving for h and then solving for c. The order doesn't matter, but typically I have a preference for certain problems. So let me reset. I'm going to set these two equal to each other. Now we're done with the calculus and just moving on to the cleanup stage. Okay, I'm going to prefer with natural log to solve for c first. This feels a little bit cleaner if I can do that first. So I'm going to raise both sides, e as the base. So sorry, e and natural log will cancel out, so I can drop that absolute value. And then also this e to the sine of 1/2 t plus c, this addition sign in the exponent location can be dropped down as the multiplication of e to the c. And I know that e to the c is just one giant coefficient c. I can just pull that out in front. Drop the absolute value because we know the c will absorb the plus and minus that's going to come from it. And then my final step is to solve for c. So I'm going to take the order pair that they gave me, 0, 4. Zero in for t and 4 in for h. Okay, we know sine of 0 is 0. E to the 0 is 1. So I have 4 is equal to c plus 1. So therefore, c is equal to 3. I'm going to go back and update my general equation, replacing the c with 3. Okay, number 4. Also non-calculator. Okay, the graph of a differentiable function f So smooth curve, slope is defined. Has a horizontal tangent at x equals -2. So at -2, this is telling us that there's a slope 0 here at the top of this curve, and is linear for 0 to 7. So the graph is going to turn into a linear graph from 0 to 7. So here it's a curve all the way up to 0, and then after this point, it's just going to be a diagonal line. Let R be the region in the second quadrant bounded by the graph of f, the vertical line x equals -6, and the x and the y axis. So the shaded region here has an area of 12. Okay. The function g is defined by g of x is the definite integral from 0 to x of f of t dt. Find the value of g of -6, g of 4, and g of 6. So if they give you a definite integral definition, there's no final equals initial plus displacement. They're not giving you an anchor point, so you just plug directly into your formula. Okay, so yeah, so there's a definite integral formula, no final equals initial plus displacement. It is just this formula. There is no anchor point. All right, so part A. Okay, g of -6 first. So -6, I'm going to place -6 in wherever the x is located. So it's going to be the upper bound. Now, I know I have to use the graph to help me accumulate displacement there, but I want to read the graph from left to right. So right now it's presented to me as from right to left. So I'm going to flip the bounds so that I don't have to change the signs with everything that I'm reading. So I'm going to adjust the signs to make it a little bit easier for me to read off of the graph. Okay, so I'm going to figure out the area between -6 and 0. And then from -6 to 0, sorry, -6 to 0 is actually over here. And we know the definite integral here is going to be, it's above the x-axis. We know it's going to be a positive 12. So if we put a positive 12 in here, we have that negative waiting for it to change it back to the appropriate sign. So the negative will stay, but we know from -6 to 0, we read from left to right above the x-axis, so positive 12. So with a negative that's still in front, so -12. Next up, there's 3 parts to part A. We also have to also find g of 4. So g of 4 is, going back to the definition, is from 0 to 4. Now this is to the right of the y-axis. So from 0 to 4, we know this is just going to be a diagonal line. We have a triangle here. We just have to find the area of the triangle above the x-axis, so let's be positive. So 1/2 base times height. 1/2. 4 is the base, 2 is the height. So that's going to get us 2 times 2, which is 4. Okay, next up, g of 6. Definite integral from 0 to, again, replacing 6 into the x. The x happens to be located in the upper bound. So from 0 to 6, we know we're going to be adding these two areas together, but we know that this is below the x-axis. So we expect a negative out of that, right? So 1/2 base times height is 1, but it's below the x-axis, so we're making that adjustment to be a -1. So +4 minus 1 be 3. Part B, for the function g defined in part A, so we see that g function there. Find all the values at which the graph of g has a critical point. We know critical point comes from where the g prime, the derivative of g, is equal to 0. So let's find the derivative first, and then we can set that equal to 0. So again, there's my g of x. If I want to find the derivative, I'm just going to say g prime, and then the right side is really just the derivative of this notation, and we should recognize this as second theorem. You know, g prime. These two operations cancel out. I'm just left with f variable replaces to be x as well. So g prime is simply f. And we just want to find where g prime is equal to 0, right? Because we know critical point ultimately is setting the derivative of g equal to 0. So we'll set g prime equal to 0. So our critical point is basically going to exist whenever our f of x is equal to 0. That's going to be where our critical point is. And if I'm looking on the graph to help me locate, okay, where's f of x going to be equal to 0? That's basically the x-intercept, right? So f of x, this is my f of x graph. F of x is going to be 0 at 4. So that fulfills the condition. We know our critical point is where g prime is equal to 0. G prime is the f. And since we have the graph of f, we can make that connection. So f of x equals to 0 when x equals 4. So we found the critical point, and that's all we need to find. Okay, part C. The function h is defined as h is the integral from -6 . Okay, question?
For part B, do we have to write anything else for give a reason for your answer? Is the f of x equals 0 when x equals 4 enough?
Yeah, it's a good question. It's enough because it's only asking for a critical point, and critical point is where the derivative is equal to 0. And so that's enough. If we just show that g prime is equal to 0, and it's not asking for whether the critical point is a relative max or relative min. So I believe that's enough, but let me do a quick check so I can get that confirmation.
Okay, thank you.
Thanks. Yeah, the scoring guideline just says G prime equals f of x. We know that G prime is equal to 0 and 0 is equals f of x when x equals 4. So yeah, you don't have to go through a full detail sentence since it's only asking for the critical point. So there's just wanting you to connect that G prime is f of x, and we're looking for where fx equal to 0. Yeah, but thanks for asking. Okay, part C. We have an h of x function, which is defined differently than g of x, but still involving the f graph to some extent, but it's now the integral of the f prime. So find h of 6, h prime, and h double prime of 6. So we're going to just step through our definition one by one. Okay, let's first find h of 6. We can just use the function that they provide for us to do that. So h of 6, integral from -6 to 6 of f prime of t dt. Now this one could potentially trip some students up because they're like, well, can I just do the same thing that I did before? Can I just find the area under the f graph? But this is not, it's not asking for the area under the f of t graph. It's asking for the area of the f prime graph. And so we're kind of, this feels a little bit, you feel a little stuck here because you're like, well, this is not the f of x graph. So how can I use this to help me get to the value I need? So we got to do a little bit of rearranging here because we're not going to be able to read the graph in terms of the area. We may have to turn this into a different version, a different form before we can evaluate. And this is where, what if we can get this to turn in terms of f, right? We don't have f prime in front of us, but we could turn this into f if we use first theorem, right? So this is an application of first theorem here. So we know first theorem says the integral from a to b of f prime is just uppercase f of b minus uppercase, or sorry, f of b minus f of a. So f prime will turn into f. So we can do that same thing here. We can transform this f prime in terms of f. We can drop the integral and make it rise up in terms of that. So if we follow this definition here, we can make f prime rise up to f and then plug in our upper bound minus lower bound. Okay. College Board AP exam, they love first theorem, so you're going to see multiple applications of this throughout your FRQ. So you can expect to see some variation of this showing up on your exam. So f of 6, now we can read the graph a lot easier, right? F of 6 is simply -1. F of -6 is 0.5, and we can just follow that and subtract those values. So f of 6, again, is -1. We're just pulling the order pair off of the graph. And then f of -6 is 0.5. We're just subtracting it, and we get -1.5. Okay, so that gets us h of 6. All right, next up, h prime of 6. Well, h prime of 6 is at the derivative level of h. So let's make our way down to h prime of x before we involve the 6. So we know h prime would be requiring us to take the derivative of this notation. We know these two operations cancel out. Just the upper bound gets plugged in. So we're just having f prime of x. So h prime is simply just f prime. So should be a easy connection there. So that means h prime of 6 is simply f prime of 6. If this is the f graph, then f prime of 6 is just the slope of the f graph at this point. And this is a linear graph, so if I can find the slope of this line, then I can find the slope at that point. So I'm just picking 2 points here. This looks like a slope of down 1 over 2, a slope of negative 1/2. So I'm just looking at that line and recognizing that the line has a slope of negative 1/2. That's the second part of what they're asking for. Finally, part C is asking for h double prime of 6. Well, to get to h double prime of 6, let's first find h double prime of x. We know h double prime of x is just simply f double prime of x. So therefore, h double prime of 6 will be equal to f double prime of 6. Now, we already know that f prime of x is negative 1/2, right? We know that this slope is already negative 1/2 all the way through, right? From one end to the other. So the slope or the derivative of negative 1/2 is just going to be 0, right? It's going to be 0. Because we're already sitting at a constant. So constant's derivative is just going to take us all the way down to 0. Okay, number 5. Consider the curve defined by the equation x squared plus 3y plus 2y squared equals 48. It can be shown that dy dx equals negative 2x over 3 plus 4y. There is a point on the curve near order pair 2, 4 with x coordinate 3. Use the tangent line to the curve 2, 4 to approximate the y coordinate at this point. So this is basically linear approximation. We're going to build our tangent line at this order pair. So we can take this order pair, plug into the derivative, find the slope, build our tangent line equation, and then we can use the tangent line equation to approximate the y value when we plug into 3. Okay, here. Actually, I'll put it in here. Okay, linear approximation. So we're going to find tangent line equation first. Point 2, 4. Slope. We know slope comes from our derivative. This is my derivative equation. I'm going to just plug 2, 4 into my derivative. 2 in for x, 4 in for y. Okay, there's my ordered pair, there's my slope, point slope form. Let me get y by itself. So once I have my tangent line equation, I'm going to now do my linear approximation. So I can plug 3 into my into the x and get my approximated y value. Now, the good thing is this is non-calculator. You can leave your answer like this. There's no need to clean this up. I just realized that 3 minus 2 is 1, so I can make it a little bit cleaner, but any of these is fine. You don't have to go any further than that. Part B, is the horizontal line y equals 1 tangent to the curve? Give a reason for your answer. So this is basically trying to ask about the horizontal tangent. Okay, so here is how, especially if there's a derivative and numerator and denominator involved, just want to give a reminder about horizontal and vertical tangents. So to find horizontal tangents, basically where the graph is going to show a slope of 0, you're going to set the numerator of your derivative equal to 0. That's how you can find that potential location. So we have our dy dx being negative 2x over 3 plus 4y. So if we want to target horizontal tangent and we want to set the numerator equal to 0, that's the piece that we want to look at. We want to look at that negative 2x. So we're just going to set negative 2x equal to 0 and see if that will help us locate a point on the graph. So negative 2x equal to 0. If I solve for x, I get x equals 0. So if there's going to be a horizontal tangent, it would have to be at x equals 0. And they say that is the horizontal line y equals 1 tangent to the curve. So that must mean if there's going to be a horizontal tangent, it must occur at the point 0, 1, right? X equals 0 and y equals 1. So that means if there's a horizontal tangent, this ordered pair would have to be on the curve. And that's a question mark because we have to verify, does that point even live on the curve? Let me phrase it a different way. Yeah, is 0, 1 even on the curve? Well, if we have an equation that can help us locate order pairs, so let's plug 0 in for x. And 1 in for y. And we see that that point is clearly not living on the ordered pair, because if it were, then we should be able to get something that agrees. But instead I get 5 equals 48, which is not true. So we don't have a horizontal tangent. no horizontal tangent at y equals 1 since the order pair 0, 1 does not exist on the curve. 3 plus 2 does not equal 48. The second part, part C, the curve intersects the positive x-axis at the point root 48, 0. Is the line tangent to the curve at this point vertical? So now it's asking about vertical tangent. And vertical tangent is basically the other side of the fraction, setting the denominator of dy dx equal to 0. So for part C, find the vertical tangent on a curve, set the denominator of your derivative equal to 0. So there's my derivative equation. I locate my denominator. I'm going to set that equal to 0. Oh, sorry. Yeah, we could do it this way, or they're actually giving us a point. So if there is a vertical tangent, then this should cause the denominator to 0 out, right? If there's a vertical tangent, then the slope should be undefined. So all we need to do is to plug that root 48, 0 into the derivative and see if it's actually causing us to get a 0 in the denominator. But I get -2 times root 48 over 3 plus 4 times 0. And this is clearly not giving me 0 in the denominator. I still have a 3 left in the denominator. So basically, we can just say no vertical tangent at point root 48, 0. Yeah, we'd have to go through this process. I mean, we probably can arrive at the same conclusion, but it's just easier and faster to just, because we know what has to happen. If it's truly a vertical tangent, this order pair should cause my slope to be undefined, but I'm not getting an undefined slope. I'm getting something that is a real number. Even though the 4 goes away, the 3 is still there. Okay, part D. For time t is greater than or equal to 0, the particles moving along the curve defined by the equation y cubed plus 2xy equals 24. At the instant the particle is at 0.42, the y coordinate of the particle's position is decreasing at a rate of 2 units per second. At that instant, what is the rate of change of the x coordinate of the particle's position with respect to time? So we talked about this, right? That sometimes FRQs like to hide related rates inside a portion of your FRQ, and that's the hint. If they ask you for with respect to time and they're giving you, a bunch of data about that derivative, then we should be thinking related rates here as our setup. So related rates is taking our equation, finding the derivative, and everything is getting impacted by time. So every variable we see is going to produce a d over dt. So we see y variable, it should produce a dy dt. We see x variable, we should produce a dx dt. But Again, the nice thing with related rates for the most part is the only derivative rule you need is power rule. But in this case, looks like we need a little bit more product rule, but there shouldn't be like a complex, rule involving like log or log base b, or arc trig, arc tangent. It should just be power rule, but yeah, they could extend a little further and involve product rule here. So, but we should be expecting, because x and y are involved, we should be expecting dx dt to show up. We should be expecting dy dt as well. So let's work through our derivative for our equation first before we decide what needs to go into these variables. And we set product rule here. Okay, so y cubed becomes 3y squared dy dx. Product rule f prime g plus fg prime. So 2x just doesn't become 2. 2x turns into 2 dx dt, because this is related rates. This isn't just implicit differentiation here. This is underlying time impacting every variable here. And 24 also gets impacted by the derivative. The 24 doesn't stay 24. 24 goes to 0. Okay, now we can look at all the data that they provide for us here. They tell us order pair F42, so that's going to come in handy. X will be replaced with 4. Y we can replace with 2. The y coordinate is decreasing at a rate of 2 units per second, so we know dy dt. We know it's not just y, because you see decreasing at a rate and decreasing at a rate, we know it should be a negative as well. So we're expecting dy dt to be negative. At that instant, what is rate of change of the x coordinate? So we're looking for dx dt, rate of change of the x. So take all that and plug it in and solve for dx dt. Okay, 3 times 4 times negative 2, negative 24. Solve for dx dt. Oh, over 4, sorry. Jumped the gun there. I think on my key, I accidentally put dy dt. It should be dx dt. Okay, number 6. All right. Functions f and g are defined by f of x equals x squared plus 2. So we get x squared plus 2 here. And x squared minus 2x, that's the one that's below. Let R be the region bounded by the graph of f and g from 0 to 2. Again, let's see, this is again non-calculator. Right, but do not evaluate the integral expression that gives the area of region R. So we know that area of R, we should always try top minus bottom first. The majority of your area problem will probably be top minus bottom. So try that first. And if somehow that doesn't work, then maybe you can try right minus left. But I think we should always attempt top minus bottom first, because that's going to be the majority of your area problem. So part A, remember area is just the depth integral from x of 1 to x of 2, top curve minus bottom curve. So the top is the f, the bottom is the g, and then we're just moving from left bound of 0 to the right bound of 2. And just asking us for the setup. That's enough for part A. Part B, let S be the region bounded by the graph of G and the x-axis from 2 to 5. So now we're moving on to talking about region S. But region S is now the base of a solid. For this solid, at each of the cross-section perpendicular to the x-axis. So this is a cross-section problem. And the cross-section problem, they have to tell you which direction to build your segment. So this is now the base of a solid, and we're building rectangles that's going to come out of the page, but the base length is going to be drawn vertically because perpendicular to the x-axis. X-axis is horizontal, perpendicular, we now have vertical. So the volume of cross-section. First thing we do with cross-section is we build the base. The base is either top minus bottom or right minus left. But in this case, they're telling us explicitly to draw it vertically. So we're going to do top minus bottom. So top minus bottom, the top of my base length is sitting on the G. The bottom is sitting on the 0. So my G is the x squared minus 2x minus 0. So top minus bottom. I can drop the 0. All right. Next up with cross-section is we want to build the area. And the area of a rectangle here is base times height. Now, if there is a rectangle problem, they should tell you how to build that height. Either they give you a number or they give you some relationship for you to build that height. You're not gonna have to guess what the height is. They should tell you what the height is. So they tell us that the height is equal to half its base length. So this is our base length. The height is 1/2 of that. So could just build the area piece by piece. We know the base is x squared minus 2x. We know the height is simply 1/2 of x squared minus 2x. So once we have the base, once we have information about the rectangle, we're just building it piece by piece. Okay, if I merge that together, then my area is just 1/2 x squared minus 2x quantity squared, right? And now the last piece is trying to get it into that third dimension, that volume integral there. So volume, I'm going to give that third dimension integral from as far left as 2, as far right as 5 for my shaded region. And it's asking us to find the volume of the solid. I mean, it would be nice if we could just plug this in the calculator, but this is a non-calculator section, so we have to work all this out by hand, which is a little annoying, but it's doable because they're not going to ask you to do anything beyond degree 2, and this is within their limits. So we can FOIL this out, expand everything out, combine like terms, apply power rule, and then plug in upper and lower bound. The benefit of this problem is that you don't have to clean anything up. So once you go through power rule, once you plug in your upper and lower bound, you can leave all your fractional mess as your answer, and you don't have to go. You don't have to combine any of the fractional. You don't have to do like terms or common denominator. You just have to show the numeric value that represents the unsimplified version of your answer. Right. So, but we do have to go through quite a bit of cleanup here to get it to the point where we can actually do power rule. And also, if you're thinking, wait, what if we do u substitution? U substitution is not going to work because if our u value is x squared minus 2x, our derivative will be 2x minus 2, and there's no leftover x's to cancel out. So we really should be FOILing this out and relying on power rule once we clean up. Gonna distribute the 1/2 through as well. Combine like terms. All right, everything should be, oh, let me go one more step here. Everything should be nicely cleaned up for me to jump into my power rule step. Power rule for each of my 3 terms. Once I go through power rule, I can do half bracket, and then I can work in my bounds from 2 to 5. So 1/2 x to the 4th power rule comes 1/2 x to the 5th over 5. 2x cubed becomes 2x to the 4th over 4. 2x squared becomes 2x cubed over 3. No plus c because we're involving bounds. Now we can work the bounds into our antiderivative. Upper bound first. I can reduce if I want here, make it 5 to the 4th over 2 plus 2 times 5 cubed over 3 minus big parentheses. Now plug in the lower bound. Again, you don't have to clean anything up, but you do need to show how you're plugging in these numbers. Just over 2. because I'm going to reduce that to 1/2 plus. So you can leave your answer as this big mess, and that is fine. Okay, last part C. Write but do not evaluate an integral expression that gives the volume of the solid generated when it's rotated. Okay, so now you can think about this in Washer method. Now you see that rotation being involved. Okay, we're rotating this around the horizontal line, y equals 20. So let me draw the graph again so I can just. So again, this graph is from 2 to 5, something like this. And I'm taking this shaded region and I'm rotating it around the line y equals 20. It goes all the way up here. Obviously tell that there's a gap. So it's got to be Washer method. We need to build two radius, big R and little r. Big R and little r both have to extend or have to include the dotted line. So from the dotted line all the way to my furthest boundary, that'll be my big radius. And then from the dotted line to the closer boundary, that'll be my little radius. So big radius, top minus bottom. Top is sitting on the dotted line, which is 20. The bottom is sitting all the way down at the x-axis, which is 0. So 20 minus 0. Little r. Top minus bottom. Top is sitting at the 20. The bottom is sitting at the curve, which is the g of x, which is x squared minus 2x. Right? This curve is the careful that you protect the bottom with a set of parentheses. So the negative gets distributed through. And now I can put into your volume Washer method formula. Big radius squared minus little radius squared. Big radius is 20 squared. And then little radius, I can clean this up a little bit here. 20 minus x squared plus 2x. It's just asking us to write but do not evaluate an integral notation expression. So this is as far as we need to go. All right, that's all I have for the AB students. If you have any last minute questions, you can stop by tomorrow morning, 7:10 to 7:40 before your AP exam. If you have any final questions, or you can even drop off your Unit 5 and 6, your Packets 5 and 6 if you would like to. But yeah, thanks for coming to the help session and good luck. Hope you guys all do well. And then I'm going to switch over to the BC problems for BC students. Okay, so this is number 2. Back to calculator. So this is calculator question here. Particle moves along the curve in the xy plane, where x and y are measured in centimeters. It is known that x prime equals at minus t squared, y prime equals negative t plus root t to the 1.2 plus 20 at time t equals 2. Particle is at 0.36. Find the speed of the particle at time t equals 2 seconds. Show the setup for your calculation. So we know our speed formula is just the square root of x prime of t squared plus y prime of t squared. So pretty straightforward. If you know the formula, you can just plug x prime and y prime directly into the formula. Don't even have to find the derivative. It's already set up in the form that you need. So it's really just entering the calculator, replacing all the t's with 2, and then practicing and making sure you're getting that numeric answer. Part B, find a total distance. So total distance is just the definite integral of the square root here. So practice entering that in, see if you're able to get that. So I have x prime stored under y1. Then I have y prime stored under y2. (15.9017 centimeters). Find the y coordinate of the position of the particle at time t equals 0. So y coordinate, we only care about the y value, just the movement of the y value. So we have displacement of y. We have a time, an anchor point of the y value, and then we can just find the y value at time t equals 0. So we can use our final equals initial plus displacement. We're looking for y of 0. We're starting at y of 2, and then we're trying to bridge that gap from 2 to 0. If you really want to get that 0 down here, you have to change this bounds and flip the sign. Remember, your final equals initial plus displacement. These bounds need to initially match because I'm starting at 2 and I'm ending at 0. Initial and final. But I don't think you need to do that if it's a calculator question. The calculator will just handle all this for you. But if you feel more comfortable with the going from a smaller to larger, you can do that. But just make sure that when you flip it, that you're changing the sign of what's outside. But ultimately, Either way, you should get the same answer, negative 1.1736. And the reason that we can ignore the x values is because it's only asking for the y value change, the y value location.
Mr. Yang, are all the particle motion formulas on the formula sheet for BC?
Remember on your AP exam, you're not going to be given any calculus formulas. Do you know what formulas they'll give you?
Yeah, no, I meant the one on your website.
Oh, right. Yeah, I would say those are all the BC formulas on that BC sheet. Front and back. Yeah, so I think the front I had mostly units 6, 8, and 9, and then the back page I have all the unit 10 stuff. Yeah, those are all the formulas.
Okay, thank you.
Yeah. Okay, so here's part D. Between 2 and 8, the particle remains in the first quadrant. So keep in mind that's where the particle is. During the entirety of the first quadrant. Find all the times between 2 and 8 when the particle is moving towards the x-axis. So if I can somehow show that my y prime is negative or positive, then I know the particle is either moving away or towards, because I know it's going to be starting above the x-axis. Right? So if I get a negative, it's got to go towards. If it's positive, it's going to go away. So particle will move towards the x-axis whenever y prime is less than 0, since the particle is starting in quadrant 1. If the particle was in quadrant 4, then y prime is less than 0 is going to make it go away from the x-axis, right? But the particle is located somewhere here. So if it moves towards, if the y prime is decreasing, then it will move towards the x-axis. So we can make the calculator do the work for us here, and let's build our y prime to begin with, right? We know that our y of t is equal to y of 2 plus the integral from 2 to x of y prime. So, I mean, this was our equation that we built from part C, and we can adapt it for y of t. So if I want to build y prime, I just find the derivative of each term. So y becomes y prime, y of 2 goes to 0, and then the derivative of this is simply just y prime. So, and then if I just make the calculator graph y prime, actually, I don't have to go through any of this step. It's already given us y prime here. I can just plug y prime into the calculator and see that y prime is clearly below the x-axis between 5.222 and 8. And this is going to be where the particle is going to be moving towards the x-axis. So y prime. Yeah, I'm adjusting my window from 0 to 8. I'm graphing it. So I'm just looking to see whenever y prime is dipping below the x-axis, and I see once I get past that x-intercept, it's going to be all below the x-axis. So if I do second trace, 0. Pick a point to the left. Pick a point to the right. 5.222. So from 5.222 to 8, it's all clearly sitting. It's all below the x-axis. So all this is where y prime is negative, and whenever y prime is negative, that is when the particle is going to be inching towards and getting closer towards the x-axis. Okay, number 5. Function f is twice differentiable, so now we're back to non-calculator here. Function is twice differentiable for all x with f of 0 equals 0. Values of f prime, the derivative of f, are given in the table. For x is greater than or equal to 0, function h is defined as h of x is depth integral from 0 to x of 1 plus f prime of t squared. Find the value of h prime of pi. So h prime of pi, we can first find h prime of x. To find h prime of x, we can just find the derivative of that. Second theorem will lead us to that h prime is just the portion after we strip away the integral. So h prime is just square root of 1 plus f prime of x squared. Find the value of h prime. So h prime of pi is just going to be square root of 1 plus f prime of pi squared. And we know f prime of pi is 6. And 1 plus 6 squared is 37. And then root 37 is our answer. What information does this tell us about the graph? We should recognize this as arc length. So it's simply the arc length of f, of our f graph from 0 to pi. The arc length of that curved arc from 0 to pi. For C, this is Euler's method without a calculator. We want 2 equal step size, so we know that's 2 steps. That's our n is equal to 2. And we know we're starting at 0 and we're starting at 2 pi. So 0 is a, 2 pi is b. So we do b minus a over n to get our step size, which is pi. So we're starting at 0, and then next we're going to pi, and then we're going to 2 pi. So we're just going to build out our table. So 0, pi, and 2 pi, and we know that we're starting at 0, 0. And f prime is basically our dy dx. And we know f prime of 0, f prime of 0 is simply 5. Doesn't take the x value, it just takes the y value. F prime of 0 is 5, and then we do our tangent line equation, our approximation here. So y equals y sub 0 plus dy dx, which is 5, our slope, times delta x, which is our step size, which is pi, which is 5 pi. And we can update our next row with our y value being 5 pi. Next up, we want to find f prime at this order pair, but f prime doesn't need the y value, it only needs the x. So f prime of pi, again, we rely on our table. F prime of pi is just going to be 6. That's our slope. And then we update again. Y sub 0 plus dy dx times delta x. 5 pi plus 6 pi is 11 pi. And we have our destination. We have the y value when x is 2 pi, and our approximation is 11 pi. Part D, find the indefinite integral rather. We probably try u substitution first, and we realize, okay, not able to quite find a u value that will work. And we know that this is a BC exam, so we should be expecting some BC topic to show up, and this is a good candidate for integration by parts, where we have two different terms within two different families of functions that are being multiplied together. And the nice thing is that there's no logs involved, so we should be able to apply this using tab method. Our polynomial algebraic expression is a t plus 5. Our trig is cosine t over 4. We can let our f be our t plus 5. We can let our g prime be cosine t over 4. And then we're just kind of going through our tab method here. T plus 5 goes on our first row. G prime is cosine of 1/4 t. On the f side, we take the derivative. T plus 5 becomes 1, 1 becomes 0. And then we also want to alternate our signs here. So positive, negative, positive. This side, we have to be careful here. We're taking the antiderivative, which means that our u substitution of 1/4 t is going to keep producing a 4 over and over again. So the antiderivative of cosine is sine, but the coefficient that's going to pop out is going to be 4. Then sine's antiderivative is a negative cosine. Another 4 pops up, so that becomes negative 16. And then we just pair up our diagonals. T plus 5, positive t plus 5 times 4 sine of 1/4 t, that's our first term. And then negative 1 times negative 16 cosine of 1/4 t, that's our second term, and then plus c. Okay, let's finish up with number 6. I find that this number 6 is relatively easy compared to previous number 6s that we've seen. So I'm hoping that you guys will also get an easy one like this on your exam tomorrow, but you guys will let me know soon enough after tomorrow's exam. Maclaurin series for our function is given by this f of x. The converges to f. In the interval of convergence, it can be shown that Maclaurin has a radius convergence of 6. Determine whether Maclaurin series converge or diverge at x equals 6. Give a reason for your answer. So at 6, that means I'm just plugging in 6 in for x and just seeing what this cleans up to be. So if I plug 6 in for x, I get the 6's to cancel out. 6 to the n over 6 to the n will cancel out. I'm left with n plus 1 over n squared, which if we look at this, we should be able to recognize this as, we can do limit comparison test, or you can go through direct comparison test. But limit comparison test, the comparison is with 1 over n. If we strip away the n over n squared, it's really 1 over n. And if we compare these together, limit comparison test will show that it's valid. And so because 1 over n is a diverging series, we know n plus 1 over n squared is also diverging. So let me just show LCT here. We do dividing, doesn't matter which order you divide them in, either the comparison partner with the function with the original, or the original with the comparison partner. Either way, as long as our limit can show a real number, technically it should be the absolute value. So it should always give us a positive real number. If it does, then we know that these two will share the same behavior. And because we know 1 over n is a diverging harmonic series, by limit comparison test, this must also diverge as well. Part B, it can be shown that f of -3 is given by this function here, and it cleans up to be this, n plus 1 over n squared times -1/2 to the n. Notice that there's an alternator here, and that the first three terms of the series sum to s sub 3 equals -125 over 144, show that the absolute value of f of -3 minus s sub 3 is less than 150. We should be able to, 1 over 50. We should be able to recognize this. Oh, this is an error bound here. Is it Lagrange or is it alternating series test? And we can tell there's an alternator here. This is a converging series. We should be looking at alternating series test, which means we know that the first unused term will give us the error of this polynomial. So all we need to do is look at s sub 4 and see if s sub 4 is less than 1 over 50. If s sub 4 is less than 1 over 50, we know that our error bound is clearly under this accuracy, or is better than this accuracy. So to find the fourth term, just plug 4 into your rule of sequence. And if I plug 4 into my rule of sequence, 4 plus 1 over 4 squared times -1/2 to the fourth, that cleans up to be a number that's less than 1 over 50, and we're safe. We have a safe upper bound that is under their limit that they've established. And part C and D are nice. You're just doing ratio tests for both of them. And they're not even asking you for interval of convergence. They're just asking you for radius of convergence. So take your a sub n and create your a sub n plus 1. So there's my a sub n plus 1, adding 1 to every n that I see. And then dividing by my a sub n, which is the same thing as multiplying by its reciprocal. Do a whole bunch of cleanup. The only thing left is absolute value of x over 6 is less than 1, which is absolute value of x less than 6. This is basically in the form of absolute value of x minus c is less than r. If I get into this form, I know that this number here is my radius. My interval of convergence is more like between -6 and 6, but we don't have to test the endpoints. We don't have to do any interval of convergence because it's only asking for the radius. Part D, they're giving us another rule of sequence. We're doing ratio test again. Replace every n with n plus 1, divided by a sub n, which is the same thing as multiplying by the reciprocal. Do your steps of cleaning up. And a bunch of x's cancel out. The only thing you're left with x squared over 3 is less than 1. X squared, absolute value of x squared is less than 3. You get it into the form of absolute value of x is less than square root of 3. This is also in the form of absolute value of x minus c is less than r. And again, my radius is this number here, which is root 3.
For part C, when you're finding the general term for f prime, are you just getting the derivative of like the x to the n, and you're like ignoring everything else?
Oh, right. Yeah.
Okay.
Hold on, let me just double check. This one. Yeah, so I'm really only doing a derivative of this x here. So all these are just coefficients. So I'm just bringing that n down. And then, wait. Yeah. I'm just bringing this n down and then subtracting 1 from that n. And everything
so
is going to stay.
Maybe
Gotcha.
please quickly walk us through how you do that. Just
Sure.
walk us through how you would
Mhm.
get the derivative of the general term.
Sure. So this is 6 part C. This is my F. I'm just going to separate it this way so that it makes it a little bit easier to see that this is just coefficient, and that's really the function that I'm finding the derivative for. So my derivative is just going to be, my coefficient is going to stay. And then just doing power rule for that, bring down the n, and the x to the n minus 1. If I clean this up, I can write it this way. And then I can do a ratio test off of that.
So
Okay.
everything
Thank you so much.
everything related to n, we can essentially treat as a constant when we're
Yes.
doing. Okay, that
Yeah.
makes sense.
Good. It's the x that's getting impacted by power rule.
Got it. Okay, that makes so much sense. Thank you.
Yeah, thanks for asking that. All right. Good luck, everyone. If you're doing some more studying, then hopefully you'll be able to feel good by tomorrow. And then, yeah, best of luck tomorrow. Would love to eventually hear feedback about how you guys felt, but one thing at a time. Hope you guys get some rest. And yeah, good luck.
You've been legendary. Thank you so much.
Thanks, guys.
You've been an awesome teacher.
Thanks
Thank
for
you,
a
Mr.
great
Yang.
year. Appreciate it.
Thank you, Mr. Yang.
Thanks
Thank
for
you
all
so
your-
much, Mr. Yang. Good night. Thank you.
Yeah, good night. Thank you. Bye.
Yep, thank you.